Hello and welcome to the final part of Lesson 10. In the previous parts of this lesson, we formed the integral Maxwell equations with respect to both path strain and path strain rate. These expressions allow us to write an explicit equation for stress, which is something that we'll use in the next lesson to address the shortcomings of what is essentially quite a simple rheological model. The final part of this lesson examines a generalized form of these integral constitutive equations that we call the Generalized Linear Viscoelastic Model, or GLVM. Now, the GLVM allows us to use these by now familiar integral functions with different types of material properties and different types of physics. So let's see how we do this. Let's start by reminding ourselves of the results from the previous part of this lesson. We saw that the integral Maxwell equation could be written in one of two ways. It could be written with respect to path strain rate. Here on the board is the result for path strain rate, and there in yellow is gamma dot of t dashed. And remember, t dash is a quantity that we call past time, and past time varies between the dawn of time, back at past time is minus infinity, and ends up now at current time at t. So gamma dot of t dash is effectively my strain rate history and takes into account all the various deformations that the material has experienced over its existence. In curly braces, g of exponential minus t dash over lambda are the material properties of our Maxwell element. So we've got our modulus g, we've got our relaxation time lambda. And the way in which it's formulated with respect to current time and past time means that current deformations are reflected in the state of stress very strongly, but deformations that happened quite a long time ago only contribute marginally to the current state of stress now at current time t. And so as current time increases and ticks on, those deformations become less well remembered, for want of a better way of putting it. We also saw that we could write the Maxwell integral equation with respect to path strain, and there in yellow is our strain, gamma of t dashed, and gamma of t dashed allows us to track strain at each integration step. And again, it gives us an explicit equation in terms of stress, and the reason why this can be useful, as you'll see in the next lesson, is that there are certain physical descriptions that we can add to this model to make it nonlinear, which allows us to capture phenomena such as shear thinning under steady shear. And those phenomena are strain related, and so we need to be able to calculate a constitutive equation with respect to strain rather than strain rate. So the key here is that stress is calculated as a function of two things. Stress depends on a measure of the deformation due to flow, those quantities in yellow, the strain rate and the strain. But of course, stress also depends on the nature of the material, and so all the material properties, written on the board in pink, are grouped together to make that explicit. Now, this idea of separating out the deformation due to flow terms and the material property terms can be generalized, and that is where we get our generalized linear viscoelastic model from. So let's put the result for integral Maxwell with respect to path strain rate back on the board, and also its equivalent in terms of the generalized linear viscoelastic model. All we've done here is create a new quantity, big G of t dashed, that captures all the material properties. And in this case, big G of t dashed is simply what is contained in the curly braces on the left-hand side of the board there. So it's a function of my modulus G and of my relaxation time lambda, G e to the minus t dashed over lambda. And that becomes big G of t dashed. We can also do the same thing with our integral expression with respect to path strain. And the way we write that is we now have big M of t dashed, where big M of t dashed again simply is another way of phrasing the properties that are inside the curly braces on the left-hand side there. So it's everything to do with the material, nothing to do with the flow. Now, big G and big M have names. big G of t minus t dashed is called our relaxation modulus. Big M of t minus t dashed is called a memory function. And all we've done here really is formalize that split between material properties and the deformation due to flow. But of course what this allows us to do is to write different expressions for our relaxation modulus and our memory function for different constitutive laws that involve slightly different physical descriptions of how materials behave. And it keeps the material description very clear and distinct from the flow deformation description. Now, remember, these are linear models. We know that integral Maxwell, which is a linear model, predicts a Newtonian viscosity in steady shear, and the same is absolutely true for the linear viscoelastic model as well. So let's just formalize that. There is the general linear viscoelastic model written with respect to past strain rate. There we go, gamma dot of t dash, gamma dot of past time. Let's say now that the only deformation this material has ever experienced is just steady shear. So gamma dot of past time is just a constant. Let's call it gamma dot 0. It doesn't change. It has no past time dependency. Since it has no past time dependency, we can take that flow deformation part outside of the integral. So now stress as a function of time is just a constant gamma dot 0, and then the integral of my relaxation modulus with respect to past time. If you remember our definition for apparent viscosity is simply stress divided by rate of strain, then we can see that the apparent viscosity is just an integral that is solely dependent on material properties alone and has no dependency whatsoever on the deformation history of the material. And so our apparent viscosity is in effect independent from our flow deformation, hence it's a steady shear viscosity. However, the general linear viscoelastic models do allow the easy incorporation of extra pieces of physics that allow viscosity to finally become dependent on deformation history, but more about that next lesson. So, we can use these relaxation moduli and memory functions for different rheological models, as I've said before. So let's just illustrate that with an example. You've met the Maxwell equation in differential form and in integral form, and here on the board, highlighted in green, is effectively differential Maxwell. You've got tau plus lambda 1 d tau by dt equals eta naught gamma dot. That's differential Maxwell. However, there's another model which builds on differential Maxwell called the Jeffreys model. And we can see here the Jeffreys model also includes an additional term that depends on the derivative of the rate of strain, so how quickly our deformation is changing, and associated with that is an additional relaxation time lambda 2. Now, we're not going to go through the derivation of this result, but the relaxation modulus from a Jeffreys model can be written thus. The terms in green there are the ones that are retained from Maxwell, and the terms in pink and yellow are those additional terms that are added to the relaxation modulus as a result of using the Jeffreys model. There's a slightly curious term on the right-hand side there, in pink and yellow. You've got 2 eta naught lambda 2 over lambda 1, and then delta of t minus t dashed. Delta here is the Dirac delta function. It's a unit impulse. Let me just sketch out that. If we're to sketch out a unit impulse, what that means is that a unit impulse is 0 at every time that x is not equal to 0. But when x is absolutely equal to 0, my unit impulse has a height of infinity. If we look at another property of the Dirac delta function, if we integrate it, if we sum up its contribution over all x, what we find is that it relates to a step function. If x is less than 0, our step function is 0. If x is greater than 0, my step function is 1. At 0, my step function is actually equal to a half. Now, if we think about what this means in context of the relaxation modulus in the middle of the board there, that right-hand term involves my impulse function of t minus t dashed. T minus t dashed, if we think about this, what this means physically, is current time t, now, minus a measure of past time, and we know that past time is our variable. So current time minus past time is always positive. So delta of t minus t dashed is always positive, which means that that is always equal to 1. Except for when past time equals current time. That's when delta of t minus t dash is going to be equal to 0. So at that point, my integral of my Dirac delta function, my step function, is going to equal to 1/2. And I'm talking about the integral of delta of t minus t dash because, of course, we end up integrating our relaxation modulus with respect to past time. And so whether or not that includes our measure of deformation depends on whether our deformation has been steady or not. So I've put that on the board as a means of an example of a different formulation of a relaxation modulus, and it will have an associated different formulation of a memory function. And if you look in the literature, you'll find lots of different formulations of both relaxation moduli and memory functions, all of which can be used in the generalized linear viscoelastic model. And so it gives now a range of choices for you in order to describe the linear viscoelastic response of a material with respect to past time. So let's recap a few key points. The integral Maxwell equation with respect to both past strain and past strain rate can be generalized to form this thing that we've termed the general linear viscoelastic model. If one looks at the formulation of these equations, the material properties are clearly separated from the flow deformation. If you look at the integral formulation with respect to past strain rate, we have something called a relaxation modulus pre-multiplying that strain rate within the integral, g of t minus t dashed. If we look at the strain-based formulation, we have the memory function, m of t minus t dashed, pre-multiplying that strain history term. The thing to remember here is that this is a generalized linear viscoelastic model, and so constant viscosity in steady shear is still predicted. However, the thing that we've alluded to all along is once we've written these constitutive equations in integral form with respect to past strain or past strain rate, we can add in additional pieces of physics that depend on past strain or past strain rate that allow these models to become nonlinear. And that's what we're going to look at next lesson.